Welcome back, friends. Sorry, has the recording started? Yeah. Okay. Welcome back, friends, and let's continue from where we left off. And now, as I said, I will move on to the writing tablet. Let me start sharing my screen. Okay. All right. So, what we will do to start with is what I just alluded to before we took the break, and that is classification by flow configuration. Okay. The first one is called, as we said, parallel flow. How do I classify that? Let us say this is my configuration, and this is my okay. So this is my hot fluid, PHI, PH exit, inlet exit, and this is my cold fluid, PCI and PC exit. Okay, the hot fluid flows like this. The cold fluid also flows parallel to the hot fluid and finally comes out of here. Okay, so this is parallel flow. And then you have what we call the counter flow. You draw the same thing here. Now, when I teach on the blackboard, I cheat a bit. I just change things on the first diagram, but here I cannot. Okay, same configuration. Okay, PHI, PHE, but I reverse the flow direction. PCI, PCE. So now the liquid, the hot and cold streams are in opposite direction, so counter to each other. Earlier it was parallel, either this or this. Now this. Okay, so this is called counter flow. And the third one, as we said, we also saw is cross flow, where they're cross with each other, so they're at right angles. So there it's a little difficult to draw in 2D, but what it essentially means is, let us say this is my heat exchanger. My hot fluid will come like this, THI and THE. My cold fluid is going to come out like this. Okay, so the most common configuration, if I can draw, is something like this. If I draw, try to draw in 3D, let us say. I'll draw one box. Another box. The hot fluid comes out like this. It comes in and let us say through the lower compartment and flows out. And the cold fluid comes in from the top compartment, comes up like this. Okay. So cold fluid at the top, hot fluid at the bottom, cross connect or physical cross configuration. Any questions on these? Because these are important ones. I mean, these are easy to understand definitely, but these have very significant, implications on what we are going to talk about after this. Okay, now I need to see a few things here. Okay. All right. The next concept that we are going to talk about is known as very important. Okay, it's called overall heat transfer coefficient. And we denote it by the term U. Very important. Okay. Now you think about it. This we have done actually. So the reason I took up heat exchangers now is because the basic concepts we all know. Now, essentially, in a direct transfer type heat exchanger, what happens? The flow, the heat exchange, sorry, happens through a wall which separates the hot and cold fluids. We have discussed that, right? So there's this cold fluid that is moving, and then this hot fluid on the other side of the wall, right? And this is my wall of thickness E. Okay. Now the hot fluid is flowing with a certain heat transfer coefficient, right? Which is H. The fluid heat transfer coefficient, which is C. And the heat transfer coefficient, we have not studied convection, but we know that heat transfer coefficient does depend on the flow rate, the configuration, whether it's flow over a flat plate, flow over a cylinder, blah, blah, blah. Okay. But right now, for all these heat exchangers as heat exchanger problems as well, these heat transfer coefficients will be given to you. So if you consider a plane wall, like we drew here, right? Like we drew here, the heat exchange is happening across the plane wall, which is this one. Right? The wall separating the hot and cold fluids. If you consider a plane wall, then overall heat transfer coefficient comes directly from the definition of series thermal resistance, right? So areas are the same. It will be 1 over Hi plus T over K plus 1 over HH plus T over K plus 1 over HC. In this case, the thermal conductivity of the solid wall. Okay. So pretty much this is equivalent and since it's a plane wall, the areas are all the same. So I could take the area out, and the heat transfer coefficient is defined, known as the overall transfer coefficient. The units are exactly as that of heat transfer, watt per meter squared Kelvin. Okay. So the watts per meter is whatever, let us say 200 watts per meter squared Kelvin. Okay. So therefore, it means that the heat when cold fluid, that Q is equal to U is the surface area A times the temperature difference between the hot and cold. Okay. UA delta T. In thinking, what is that delta T going to be? Because the temperatures always change. Yes, that's a very, very important question. And we are going to talk about that. This was a simple one. We have done more complex ones. And in heat exchangers, which is probably more widely encountered, assume a tubular configuration. Pipe inside a pipe, tube inside a tube, which is more common. In that case, what happens? The hot end of a tube. Let us consider a circular tube. Are not. Okay. Inside you have the hot fluid. Outside you have the cold fluid. So what I will write is 1 over U I I. Important. 1 over HI plus, as we know, 1 over 2 pi KL log R naught over. We remove this for time being and just write it as 1 over HA, 1 over UA. Is this. Okay. Now the question is, should be taken. Okay. So this can actually be 1 over UA. We can write it as 1 over either UI AI or 1 over U naught A naught. So which means both can be used, but clearly spelled out. Okay, what needs to be clearly spelled out. Okay, that's wrong English, but you understand what I'm trying to say. So UI AI or U naught A naught. Therefore, if somebody asks you, okay, before that, let me complete this. Therefore, 1 over UI, if I want to write it as 1 over UI, would be 1 over HI plus it should be HAI. AI, so to multiply by AI on all sides. So AI is what? 2 pi RIL, right? So this should be RI over K times log of R naught over RI plus AI over A naught is again 2 pi R naught, 2 pi RL. So this is how it is going to be 1 over HO. Or I can also write it as 1 over U outside, inner and outer, is, no, this should be Rho over Ri. Basically, you multiply this expression at the top, what we have come up with here, this expression, by A naught now. So 1 over U naught, 1 naught over Ri Hi, plus R naught over K, plus 1 over H naught. Both are correct. Okay. So therefore, it is important U in terms of outer or inner surface area. So therefore, if anybody tells you that the overall heat transfer coefficient with the hot and cold fluids in a tubular arrangement is something X watts per meter squared Kelvin, you must ask them that is this overall heat transfer coefficient based on the inner surface area or outer surface. Then somebody says, oh, it doesn't matter, you know, it's important. Okay, somebody will say, yeah, hey, it's like a 6-inch radius, and you are talking about maybe a few millimeters of thickness. That's okay. Okay. The last thing I would like to say is the above expressions are for clean surfaces. Okay, what do I mean by that? See, because in reality, as time passes, deposits occur, okay, solid deposits. Either side of the tube. Okay. Forming thin layers. Okay. It is called scaling. Okay. If you, especially for example, you know, if you take, if you oil up, sometimes use certain chemicals to, if they're really stubborn deposits. Okay. So these add additional from the thermal point of view, these introduce additional thermal resistance. Okay. So this is actually called fouling resistance. Okay, fouling of the surfaces. And these resistances are called fouling factor, and typically denoted as RF double prime, and the units are meter squared Kelvin per watt. Exactly 1 over heat transfer coefficient. Okay. So therefore, also equals to 1 over U naught A naught. Let me write it properly. Is equal to 1 over HIAI innermost plus RF double prime I divided by AI plus 1 over 2 pi KL log R naught over Ri plus so these additional terms get introduced. So you in your problem, if somebody says that there's a fouling on the outer surface and the fouling factor there is whatever x1 meter squared Kelvin per watt, this is what you have to do, outer surface. Similarly for inner surface, you have to introduce it here. Okay. And if it occurs on both, you have to consider both. Okay. So this is the final expression with fouling. The earlier expressions were for clean surfaces, as we said before. Any questions? Is it clear? This is known thing, but this definition of the overall heat transfer coefficient is very, very important. Okay. So again, we are actually building up tools, just like we did in radiation. We are defining certain things. Overall heat transfer coefficient, an extremely important definition. We've done that. Now, hand in hand, I have to define something called mean temperature difference. We call that delta T. M stands for mean. And this is exactly, friends, what we were talking about, that let us consider this wall. There is a hot fluid and there is a cold fluid. I'm drawing it in parallel configuration. What is the mean temperature difference? Because the hot fluid, the temperature is changing as you move. Cold fluid also, the temperature is changing as you move. Okay. If I take a very small section, and call this dA. Okay. So consider a differential area dA on the wall. Separating the hot and cold fluid. So what is the temperature difference? What is the heat transfer here? Of course, from the hot side to the cold side. So I can write dQ is going to be U delta T dA, where delta T is TH minus TI at that location. Sorry, TH minus TC at that location. So what will be the total heat transfer? Q going to be integral across the entire area of the plate, U delta T dA. Okay. If U is assumed to be constant, then Q is U integral delta T dA. So now let us define a mean delta T. For a mean temperature difference. In that case, delta Tm is 1 over A integral delta T dA. And Q equal to U A delta Tm. So this, my friend, is the most basic performance equation for a direct transfer heat exchanger, direct transfer type heat exchanger. Heat exchanger is often termed as HX. Okay. So therefore, my basic definition now I have three of them. Q is equal to m dot H Tph Thi minus Dhe is equal to m dot C Tpc Tce minus Tci is equal to U A delta Tm. This is also important. This is also, they're all equivalent definitions of the total amount of heat that is transferred between the hot and cold fluids. Very important. Okay. So now what is delta Tm? Okay. The next question is, how do we calculate delta Tm? So U we have figured out how to calculate, at least for basic configurations like flow, in a tubular arrangement or flow across a wall. But delta Tm, very important, right? So that is what we are going to do next, is we are going to find out the two basic configurations, parallel flow and counter flow. Okay. So we will start with parallel flow and then go to counter flow. And it's okay. To start with, we'll just start with the wall type arrangement. Parallel flow. Oh, sorry. Parallel. PCI, TCE. To reverse this arrow. Okay, so this is how it is. So now if I want to plot the temperature, let us say along the length. Along the flow length. So think about, I mean, now visualize this. My hot fluid is coming at a temperature of THI. My cold fluid is coming at a temperature of TCI. Okay. As the fluids flow, the hot fluid cools down. Sorry, please. Okay. So what happens? The temperature difference between the hot and cold fluids, which is the driving force for heat exchange, that is continuously changing along the flow. Not constant. Delta T high, and it is the minimum at the exit, delta T E. Okay. So as before, what we will do is let us take an area dA. Okay. So this is D of Tc. So this temperature rise over this length. Similar is D of Th. Okay. So I'm not writing a lot of things. You have understood what I'm trying to say. Okay. Consider small area dA over dx, length dx along flow length. Okay. So I can write dq is going to be what? U delta T W dx, where W is the width in the third. Okay. This is equation 1. Equation 2, minus m dot h Cph delta Th, sorry, dth and m dot c Cpc etc. I can write the total heat transfer in terms of the temperature drop of the hot fluid, temperature rise of the cold fluid, or the total heat transfer. Why did I take minus? Because dth is negative. Heat transferred has to be positive. If I have to write this in equality. Here. Okay, Th minus Tc at that location. Okay. So now we will go through a little bit of mathematical mumbo jumbo. D of delta T, therefore, is dth minus dtc. What is dth? Minus dq plus so this therefore I can write as minus u delta t w dx. Okay, so let us make a few assumptions. Assume u is constant along x. Okay, and hx is adequately insulated to prevent any heat loss other than the heat transfer between the fluids. Okay, so which means all heat is transferred between fluids, between the two fluids. Correct. So what I will do now is I will try to integrate this. Okay. So what I would like to do is look over here. I have d delta t. Let's write it here again. This is almost, so I can took d delta t over delta t. I can write it as d of delta t over delta t. Sorry. Minus and then plus wagera all that stuff times u delta t I've already taken out u w dx. Okay. So now what I will do is I'm going to integrate it from 0 to L, the length. So what would be the corresponding definite integral limits on the left hand side? At x equal to 0, I have delta t I, and at x equal to L, I have delta t E. That is how I drawn it. Delta t I, delta t E. Okay. So I'll write log of delta t E for delta t I is equal to minus u, and what is w dx? And this is w times L, which is A. Huh? So what can I write here? M dot Cp is what Q equals to m dot Cp delta T for each fluid. So I can write 1 over m dot Cp as minus 1 over Q times Thi minus The plus Tce minus Tci times Ua. So now take Q to the outer side. On the other side, sorry, I can write it as U times A times, I can write it as Hi Just reordering this a little bit. Minus because it was minus and I'm changing the sign. So therefore denominator I'm going to write it as delta Ti by delta To. Or Q is equal to UA delta Ti minus delta Te divided by log delta Ti over delta Te. So we wanted something in this form, right? UA times a mean temperature difference. We have got that. This is your mean temperature difference. Okay. So comparing with Q equals to UA delta Tm, which is what we wanted to do. Delta Tm is delta Ti minus delta Te divided by log of delta Ti minus log of delta Te. For very important parallel okay, but look at how beautiful it is. If I tell you a heat exchanger with the hot and cold fluid inlet and exit temperatures, this is a way to define a mean temperature difference. Okay, so it is not it is not an algebraic uh, average or basically a arithmetic mean. So this is called log mean temperature difference, or very famously LMTD. Okay, so therefore if somebody tells you, the total heat transfer is so and so much, the average heat transfer coefficient, overall heat transfer coefficient is whatever x watt per meter squared Kelvin, the area is known. So therefore, you can find out what is the log mean temperature difference. If you find out log mean temperature difference, and let's say some other temperatures were given to you, you would be able to find out one of these, an unknown temperature. Okay. So the entire, my friends, the entire solutions of or to heat exchanger problems moves around these three. As of now, whatever we have taught, these three expressions, equivalent expressions for total heat transfer: the m dot Cp delta T of the hot fluid, m dot Cp delta T of cold fluid, and UA times the mean temperature difference. Okay, so the log mean temperature difference for a parallel flow heat exchanger is this. What you are seeing is how easy to remember, right? The temperature difference between the hot and cold fluids at the out inlet minus that at the exit divided by the difference of their logarithms. Okay. Second one is counterflow heat exchanger. So this one I'm not going to derive in that much of details. Let us draw it and understand what it is. I'll draw exactly the same thing again. Same configuration, that is. In the first case, as before, let us say, did I draw the hot fluid at the top last time? Yeah, at the top. Okay. Same. So the hot fluid, CHI, CHE, M dot H. But instead here, the difference is the cold fluid, I am reversing the direction. PCI, CE. So here, my friends, what will happen is if I draw the temperature profiles along it, then it's going to be similar. Okay. In the sense, the hot fluid doesn't change. PHI. Let us say this is PHE. Okay. The cold fluid, however, instead of coming in from here, it is now coming from the left. So the inlet temperature is at x equal to L. PCI, and then what happens is it rises. PCE. So here actually the temperature difference, I'm just at a cursory glance, the temperature difference between the two fluids along the flow length, if you look from 0 to L, does not vary as much as before. Like in parallel flow, it's the maximum at one end and minimum at the other end. Here, it's not maximum and minimum that way. And depending on the mass flow rates of the hot and cold fluids and their specific heat, the temperature difference at x equal to 0 can be larger or smaller compared to that at x equal to L. I have drawn it to be smaller, but not necessary that it has to be. Okay. So I'll define this as delta T L and this as delta T of 0. It's difficult to say inlet or exit because the inlet and exit are at the opposite ends for the two fluids. So if you now go through the same expression here, the same procedure, except there will be a little bit of plus and minus sign, but you know this. You go through the same procedure, you will get delta Tm will be delta T0 minus delta TL Okay. Think about it. It's exactly the same expression. However, this is not phi minus Tci. This is delta T0 is not the difference of the inlet temperatures. So the best way to remember is for parallel and counter flow, it's the same expression. What I've written here, delta T0 minus delta TL divided by the logarithmic, the difference of the logarithm of the temperature difference at the two ends. At the two ends, 0, L. Now, at the two ends, what are those two temperatures? That just from knowing what is parallel and counter flow, you can very easily say that. For parallel flow, delta T0 is the difference of inlet temperatures and delta TL is the difference of the outlet temperatures. But for counter flow, it is the inlet minus exit, inlet of fluid 1 minus exit of the fluid other at one end, and the exit of fluid 1 minus inlet of the fluid 2 at the other end. So this is the way to remember. Otherwise, these are very similar equivalent expressions. Okay. We will take a special case. M dot H CPH, M dot C CPC. If that is the case, what happens? This implies that delta T of H is equal to delta T of C. Okay. So for counter flow, or THI minus THE is equal to TCE minus TCI. So for counter flow, it means that delta T0 equals to delta TL. So THI minus TCE would be THE minus TCI. Sorry. Hmm? So what is delta TM? So we get a 0 by 0, okay, which is indeterminate, right? But what happens if you use the L'Hospital's rule or L'Hopital's rule? Please do that and tell me what it does. Oh, 9:59. Okay, let's stop here. And we will continue from here tomorrow. So that would be a good segue. So let me stop here. And as usual, I'm going to stay back for some minutes, a few minutes, if you have any questions. But you are free to leave now. Okay, and let me stop the recording. We are going to meet again at 10 a.m. tomorrow.